Okay, so welcome to this discussion session for the first practical exercises. So this was meant to, teach you a bit about properties of programs running on Unix, but very similar things happen on Windows too. And things on the internals of a structure of a program, on memory layout, and so on, that are really relevant on the one hand for operating systems when you, try to actually implement things on an operating system or just try to debug what might be going wrong in such a system. And for compilers, obviously, you need to generate code that works with structures for storing variables. So if you have global variables in a programming language you want to compile, you need to know where to put them. You need to know how to build stack frames for a compiler. So I thought that would be a nice exercise and would even teach those who have programmed a bit in C before maybe some details they haven't heard so far. And if you've heard all of this, well, perfect, then you're excellently prepared for these courses. So there was one big question with some sub-questions, and we were asking you to consider recursion in C. So you were asked to write a very simple C program that you should call rec underline sum.c, but we're not really insisting on that name. And the C program should just calculate the sum of the numbers from 1 to n. Now, this is, of course, very easy doing it iteratively, but that wouldn't show the problems that can show up when doing it. So we wanted you to write a recursive function, so a function that calls itself again to calculate the sum of the numbers 1 to n. So a call to sum n of 5 should return 1 plus 2 plus 3 plus 4 plus 5, which is 15. And after calling the function, you were just asked to print out its return value like this. So you should be able to use the printf function and to look at the value. So we've discussed printf already in the C crash course. So the most unusual thing about printf may be these format strings percent, something like %d for a decimal number or %c for a single character, which then refer to the additional parameters you pass to printf after this first parameter, which is called the format string. So let's look at a solution I wrote for this exercise. So I hope it doesn't contain too many errors. So here we have our very simple program. And here we start first with, it's interesting, on screen sharing, my nice virtual laser pointer can't be seen, so I just use a mouse pointer. So we start here by including our standard io.h header file. We need to do this because the declaration of the printf function is contained in standard io.h. So in order to make the compiler happy, so the compiler actually doesn't print a warning about an undefined function, we're including standard io.h. And then first, let's take a look at this main function here. So main doesn't get a parameter, so it's void. And main always needs to return a value, so it's int. So I was a bit sloppy here because I'm not returning any parameter here, so my compiler might have complained, or yours with a warning like an int function should always return a value. Well, in this case, we don't have any meaningful value to return, but usually you should at least go save and include a return 0 or something at the end. So we wanted to calculate the sum of numbers from 1 to a given n. So we declare an integer variable here and initialize it, for example, with the value 100,000. And then we can directly use the result of the call to sum n, this recursive call, in the printf function as an argument. So sum n returns an integer, obviously. This integer is passed to printf. So printf has a format string that says, okay, the sum of numbers from 1 to, and then we have the first format qualifier, %d, which prints just our n, and then is %d. So the second %d prints the return value that is returned by sum n when we call it with our parameter n. So how do we do the recursion? Now, this is happening here in int sum n up here. So it gets past this parameter n and it returns another integer. And what we do is we just count down from n to n-1 to n-2 to n-3 and so on and so forth until we reach the lowest number in our sum, which is 1. So here we need to provide a condition to terminate our recursion. That is different to the theoretical exercise where we had an endless recursion. So here, if our parameter n, that is passed eventually to some n, equals 1, we just return n. We could have also written return 1 because n is 1 at this exact moment. We know this. So if n is something else than 1, well, then we have to do a recursion. So we have to calculate the sum of n plus the sum of all the other numbers from n minus 1 down to 1. And that's exactly what we're doing here. So we're calculating the value n plus, and then a recursive call to calculate the sum of the next n minus 1 numbers. So that's a classic recursion, and this works quite well for 100,000 on my machine here. So if we save this file in the editor using a file name rexsum.c, we can compile it, for example, on the command line like this. So we call our compiler like gcc -o tells our compiler, please generate an output file with the name that just follows the -o. So we call our executable just rec_sum, and then our source code file is rec_sum.c, and then we can execute it. So this -- before anything on the command line just means the shell is told to look for the executable in the current directory. So on Unix, like on Windows, you have two shortcuts for the current directory, which is just a dot, and also for the parent directory of the current directory, which would be two dots, so ... And then you just use a separator. So on Linux or Unix, it's a /, and you've probably also seen if you've used Windows. On Windows does it the other way around, so Windows uses a \. So essentially, when we run this on a Unix machine, we would execute rexsum if GCC successfully compiled without any error messages. And then we get an output like the sum of numbers from 1 to 100,000 is this pretty big number here, which I'm not going to read to you. All right, perfectly fine, right? This is your recursion program. Now, of course, the next question we asked you is to try experimenting with these values for n. So is there any situation we can find where it might go wrong? And let's just try to change n, the value of n, from 100,000 to 1,000,000. So this was our first output here, which successfully calculated the sum of numbers from 1 to 100,000. And when we change this in the editor and compile it again and call the rexsum, we get an output that we didn't expect. So it tells us segmentation fault 11. So 11 is obviously not the sum of numbers from 1 to 1,000,000. So 11 must be something else. So this was the sub-question A. Experiment with different, also large values for the parameter n. And for some values of n, the program fails to run correctly until its end. So it doesn't generate any expected output. And the next question obviously was, what might this value be? So at which value will your program fail? So this is actually not that easy to figure out. So I'm going to present a way to do this to you today. You don't need to provide the exact solution or this elaborate solution. So if you got a number that looks reasonable, of course, you'll be awarded the point, I'd say. But I'll show you a way how to do it systematically. So what happened here when we changed our value of n to 1,000,000 and recompiled? Now what happened, we've seen the program runs correctly for n equals to 100,000, and we get this strange segmentation fault 11 for n equals to 1,000,000. So the first thing you could do is just run Google with this text, what segmentation fault 11? And the first hit you'll probably get is Wikipedia, and let me cite Wikipedia here, even if it's not usually recommended, as you know. But anyways, this definition isn't quite wrong, so it's actually pretty okay. So a segmentation fault occurs when a program attempts to access a memory location that it is not allowed to access, or it attempts to access a memory location in a way that is not allowed. So either there are memory locations in the address space of our process which have no access at all or no mapping at all, or maybe you try to write to a memory location that is read-only, so you're denied the access, and because you tried an illegal operation, inside of your program, the operating system can only terminate your program afterwards because there's no way to correctly finish your program. So when you get the segmentation fault, you know your program performed a non-permitted memory access, and you could guess that this happens due to n being too large. Now, what is this number 11 behind here? So this information about things going wrong in programs and other things is actually passed from the operating system to the process using so-called signals in Unix. We'll take a look at signals in the operating system course later. So these signals actually have numbers, and the signal that is passed to our program when there's such a segmentation fault happening usually has the standard number 11 in the POSIX Unix standard. So that's why it's printing the 11 also. So it's a seg fault at short in Unix. So what happens in detail when we call this sum_n function with a large value? Now we've seen the sum_n function, when we execute it with a value n, calls itself recursively n times, or exactly n-1 times to be precise. And we know that functions have local variables. Now, if you look precisely, there are no local variables declared here, but there is something we have here, which is the int n parameter to our function. And this is treated like a local variable. So because each recursion of sum_n needs its own copy of n, it's also stored on the stack like any ordinary local variable. And in addition, we can have other information on the stack, especially the return address to the function that called us. So when we call sum_n first from main, the compiler takes care of putting the return address to main on the stack. So when we return from this first level of recursion, we are ending up in main again afterwards. And then we have our n, which may be 10, for example, here, if we start with sum_n of 10 on the stack. Then sum_n calls itself recursively again. So it calls sum_n of n-1, so as sum_n of 9. So we get another return address, this time to our sum_n function, because we called sum_n from inside of sum_n. And we have another copy of n for this recursive call. And this one in turn calls sum_n of 8. We get another return address, and we get another local value, and so on and so forth until we reach n equals 1. And when we return from this n equals 1, then these stack frames actually are, they're not taken away, they're just invalidated because the stack pointer moves up again. So essentially, whenever we go down a recursion, our stack grows from top to bottom, so from high memory addresses towards low memory addresses. And when we return from these functions again, these stack frames are all invalidated. So we're always at the correct stack frame for the level of recursion. So in this very simple example on the 32-bit machine, we might have 4 bytes of a return address and 4 bytes for an integer. So we will see later that it's a bit more space that is actually used in a real system. But let's just say for a value of n equals to 100,000, we use 800 kilobytes of stack space. And obviously for a value of n of 1,000,000, we need 8 million bytes. Now, of course, you say, my computer has like 32 gigs of RAM, so why can't we spend 8 million bytes on a stack? Because usually when you spend so much memory on the stack, something goes wrong in your program. So very many operating systems actually restrict the depth of the stack, so how much stack you can allocate. This is probably a configurable parameter, so that might vary between different Unix systems, between different Linux distributions, and on WSL, and so on. So when you exceed the stack size, there's a special page at the end of the stack, so down here somewhere, that actually has no access. So when you try to read or write it, you get a segmentation violation. So the operating system gets the information from the MMU that your process has tried to access this invalid memory page that's somewhere down here. And the operating system then figures out, okay, this process was doing something illegally. So what happens is this process is sent a segmentation violation signal, and this if you don't handle this signal, and we'll show in the operating systems course how to handle this, then your process is automatically terminated by the operating system because, well, you did something you were not allowed to do. Okay. So the real interesting question is, when does the program crash? So for which value of n does it actually crash? So of course, what we could do is we could write an iteration. We could start from 1 going to 1,000,000, compile this program maybe from scratch or write a loop, but that takes quite a lot of time. The more computer sciencey approach would be to use something we call divide and conquer or a bisection approach. And this means when you have one value for which you know, okay, your program generates a correct result, and another for which it fails, then you use this interval, you take the middle of it and check again, does this fail? If this fails again, well, you use the lower half of the interval and use the middle again. Otherwise, you use the upper half of the interval and use that middle again. So you reduce the size of the interval you're looking at always by a factor of 2. And that's what we did here. So essentially, we start with an interval of 100,000. This works. 1,000,000, that doesn't work. So we'll take a look at the middle, like 550,000, which is the mean value of the both. And this also gave me a segmentation fault when I tried. So we know the number n for which it fails must be between 100,000 and 550,000. So next we'll try this interval of 100,000 and 550,000, and we'll try the middle again, which is 325,000. So for 325,000, I also got a segmentation fault. So we need to look at that next smaller interval starting with 100,000 again. So we try that interval, take the middle of it, which is 212,500. And yes, for 212,500, I get a successful output. The sum of numbers from 1 to 212,500 is this still pretty big number here. Okay, so now we know, okay, the problematic value for n must lie somewhere between 212,500 and 325,000. So, well, let's try again. So we need to take the upper interval now. So 212,500 and 325,000. So the middle is that value here, 268,750. For that, we get a segmentation fault. So now we need the middle of the interval again here. And this is 240,625. And here we get an output, but something that's not quite expected. So it tells me the sum of numbers from 1 to 240,625 is minus something big. What? Negative sum if we just sum positive numbers? Well, that's something some of you experienced. So some of you wrote about this on Piazza. And what happens here is a so-called integer overflow. And this happens because any fixed size data type, like a 32-bit integer variable, can only hold a fixed amount of numbers. So it can only represent a part of your number space for integer numbers. So you can't store arbitrary big integer numbers in an integer variable. And the maximum size of this variable that you can store in there is determined by the number of bits. So if you have an int variable, which is signed, this is usually stored in 2's complement. So essentially you have this notation where you have a positive number and then you invert all the bits and add 1. This is a 2's complement. You should know this from computer architecture. And for example, 32-bit integer numbers in 2's complement have a range from minus 2 to the 31st, which is minus 2.147 billion something, to plus 2 to the 31st minus 1. So this is plus 2.1 something billion. So if our sum, which we accumulate over our recursions here, grows to larger than 2 to the 31st minus 1, then we have a value, because the computer doesn't really know that it's an unsigned number, because in assembly you don't distinguish between signed and unsigned numbers. It just sets the most significant bit. Now the most significant bit in 2's complement numbers indicates it's a negative number. So that's why our printf function that expects to print a 2's complement number actually prints this number as negative. Now, why does this happen? Well, C is built for performance. So if we checked for an overflow, for such an integer overflow, with every arithmetic operation we did, it would be much, much, much slower. So essentially, we just leave this out and say, well, the programmer should care about his data types and value ranges. So essentially, integer overflows are not caught in C. This is too much overhead, but this is also, again, we've been talking about security problems before. This is also a common source of errors. So another question, of course, that was asked on the forums, what's actually a correct result? So this is obviously not a correct result, but still our program terminates. So it prints something. So it successfully terminates. It just does something wrong. And this is different to the situation where you actually get a segmentation fault and it wouldn't print anything. All right. Note that we still haven't found our exact value where it fails, so where it starts doing a segmentation fault. So how can we do this? Because, yeah, well, running a loop from 1 to n, just trying every value takes ages. And typing a new number in and compiling is also very tedious. So, of course, some of you might have been wondering, can we find this maximum value of n automatically? So the first idea you might get is to, well, just build a loop inside of the C main function that does this bisection automatically. So I've not tried this code, so please take it with a grain of salt. So essentially you build a loop here, you call the sum of n, now with the value of the middle of the interval. So you start with an interval with a left border of 100,000, with a right border of 1,000,000, and a new n, which is actually not needed here. Well, doesn't matter. And then we try to calculate the sum of the middle of the interval. And if there is no crash, well, we take the upper half of the interval. And if there's a crash, we'll take the lower half of the interval. Wait, that doesn't work, because if something goes wrong here, our program has crashed already and would never have arrived at this if no crash situation here, because there's no way to check for it, because our program was already killed by the operating system. So that would be nice, but it doesn't work that way. Actually, there are ways to get this to work, and we'll discuss this in the operating systems course later on when we talk about signal handling in Unix more. So what our program receives, as we've seen, is the segmentation violation signal 11. And there's ways to catch this signal, as we call it, to handle this signal, and maybe to ignore it and to continue running. Let's see if this works, but this will take a couple of weeks until we reach that point in the operating systems course. But there might be ways to do it. So what else could we do to do this automatically? Well, a good way to do it would be to extend our program to actually accept parameters from the command line. And in C, as you've seen in the crash course already, you have two parameters that are passed to main. The first one is the argument counter. So this is the number of arguments passed on the command line. And the second one is a pointer to a pointer of character, which is called the, oh, sorry, that should be argv here. That's a typo. Excuse me. So that should be a v instead of a c here for the second parameter. And you see, I'm not testing all my code. So a pointer to a pointer of character means we know a single pointer to a character is a string. So a pointer to a pointer is a pointer to an array of strings. So each argument we pass on the command line is in its own array value, and this array value actually contains a pointer to the string of the text of the argument. I hope that wasn't too confusing. So what we can do now, and in real life we should check for errors so that we have a sufficient number of parameters and this parameter isn't 0. So we could take this argv element of 1. So the first parameter here, as I said, that should be a v here instead of a c. And this returns us a pointer to the string, to our first parameter. So you might be wondering, why isn't that 0? Because, you know, C arrays start at 0. Well, the 0th parameter is the program name itself. So if you use argv of 0, you get the program name. So regsum in our case, with which the program was executed, and argv of 1 would be the first parameter. Now this is a character string, so we need to turn this into a number. And there's some convenient functions like a to I. So a stands for ASCII and I for integer. So it's a conversion of ASCII to integer. This takes a character string, so a pointer to a string, and returns an integer representing the number that was passed. And we just assign this to n. So now when providing the sum_n function as before, we could just call our sum_n function with this n that was passed on the command line. And then we could write some shell script. And I'm not going into detail on writing this shell script to do this by section approach. And then we don't need to compile this program over and over again. We just need to call it with the value of n we want to experiment with. And then we can figure out, has this program terminated correctly? So did we get an output, or was there a segmentation fault? If there's interest, I can provide a little shell script to do this, but you're not expected to know a lot about this right now. But you should just know there are ways to do stuff like this. And by passing parameters here, this makes life quite a bit easier. Okay, so the next part of the question was, in addition, create a number of different variables with different types, global, local, initialized, uninitialized in your program, and print their addresses in memory in the main function. So here you should just, again, experiment with addresses and separate segments, memory segments of your program. And we've seen you can print addresses of variables using printf, using this %p for pointer type qualifier here. And then you'd have to pass this AND operator before the variable name. Before the variable name to actually retrieve the address instead of the value of the variable. So here I added in blue a number of variables like global variable A, which is uninitialized, and initialized global variable B, a global character array of 23 elements, some local variables here, and sum_n, a static int variable, a regular int variable, and in main I added a double variable just because ints are boring. So now we have a floating point variable here also. So when you try to print the addresses of all the variables in main, you might have found out that the local variables here in sum_n actually can't be printed from main. So these two printf instructions for printing the address of D and address of E, if we add them here to main, well, our compiler complains when we compile it, and it says, I've called this program rs1.c in between, doesn't matter. Use of undeclared identifier D in this print operation and use of undeclared identifier E. Now, why is this the case? This is the reason because the visibility of local variables is restricted to the function they're actually declared in. So I can only access D and E from inside of sum_n. But if I wanted to try to access them from main, there would be no chance because the compiler doesn't know about any local variables E and D here in main. So we could only print their values from inside of sum_n. Now, if you remember your C crash course in detail, you found out that there's this static qualifier, which means that the value of D should be retained across recursive or iterative, whatever calls to sum_n. So whenever sum_n is called again in the context, the old value of D that was stored in D in the previous call to sum_n would be retained. So this means D can't be stored on the stack. So it needs to have a global address because otherwise its stack frame would be destroyed and its value would be gone. So this is a very special case of a value that's not visible in main because of the scoping rules. So we say this D is a local variable nevertheless, so it's only visible in sum_n, but still has a global permanent address, so the compiler treats it as global. Oops, come on. So let's take a look at some addresses here. So when we call regsum and we remove the print of D and E, the addresses, we get a couple of numbers here printed out. We've printed them in hexadecimal here. Now, you've already seen the use of the nm tool to look at addresses. And if you call nm on this regsum binary, you see, ABC have different addresses from the ones that are printed. So you didn't have to check this, so that's some additional information. And this is, again, a security measure taken by the operating system because attackers that manage to create such a buffer overflow, as we've already seen, if they know the addresses, for example, of variables and functions, they could inject code into your running program that actually tries to override data or call functions. And what many modern operating systems do now here is something called address space layout randomization, or ASLR. And this means that the exact addresses where our variables and functions end up in memory are randomized at every program start. So an attacker that somehow attacks a running program would need to know the current random value that was chosen when the program started. And this is pretty impossible. But you see there's only so much randomization included because the last 3 hex digits, so the last 12 bits of these addresses are identical for A, B, and C. And this is to be expected because what's randomized is only the virtual memory page address of the variable. So a page, as we've seen, is usually on Intel machines 4 kilobytes in size. So 4 kilobytes is 4096 bytes. So 2 to the 12th is 4096 bytes. So you need 12 bits to address 4 kilobytes. And the last 3 digits are exactly, each hex digit is 4-bit. So we have 3 times 4, 12 bits. So the address, the relative address inside of your memory page stays the same. And just the rest of the virtual address before that is randomized. But still, there's a lot of space to randomize. So to print the addresses of D and E, as we've said, you would have to print them inside of some n, and you see this in a bit. And what you also see in the NM output, we had this static variable, static local variable D, which is only visible inside of some n. But since we have a global address for this, it shows in our NM output. But it's not called D, but it's called D.2319. So this is just a random number here. And this is because of possible conflicts. So if we had a real global variable also called D, there would be a conflict between our static local variable and our real global variable, because both would be named D. So all the static declared local variables here get some number attached to make them unique. Okay, that was going very much into details. Of course, I didn't expect you to answer the questions on that level of detail, but I thought you might find this interesting. So let's go on. The next partial question was, which distance in bytes do the addresses of 2 variables have that are declared one after the other in main? So here I declared 2 variables, a double variable, so a floating point variable with double precision called f, and an integer variable as before, n, which we initialized. And then we can call our regsum program again that prints the addresses, and we can take a look at the addresses of f and n. So we see first we have f on the stack. So f had this address of 7, ff something, 5, f0. So especially for operating systems, it's really good to be able to work with hexadecimal addresses in your head. So if you need some practice with this, I can only recommend looking at numbers and printing numbers in hex. And our integer variable n has the address, well, the same digits before, and then it ends with 5EC. So this is expected because our compiler here allocated the variables as they came on the stack. And remember, the stack grows downwards. So first it tries to allocate memory for our double variable f, and then it decrements the stack pointer by the size of our integer variable here. So it decrements it by 4 and then allocates space for our variable n on the stack. And if you use a hexadecimal calculator and calculate the difference between blah, blah, blah 5f0 and blah, blah 5ec, you will find out that the difference is 4. So our variable n occupies the addresses 5ec, 5ed, 5ee, and 5ef, which is 4 bytes because it's 32 bits, 4 bytes big. And after that, the bytes representing our variable f, our double variable, start at f0, f1, f2, and so on. All right, so because there was some question on Piazza how to calculate the difference between 2 addresses, well, that's exactly the way to do it. You interpret the address, so the pointer to this variable, just as a number, in this case a hexadecimal number. It would of course work as well if you just printed it as a decimal value, and then you subtract the 2 addresses from each other, and then you get the distance in bytes for the starting byte of each variable here. So what happens, because this was very regular, what happens if we add another character variable g, for example, in between f and n? So this is an extension that wasn't really asked. but maybe some of you have tried. So we have a double F, and then we have a character G in between, and then we have our integer. So if we print the addresses now, we see F is at FD0, G is at FCB, and N is at a higher address than G. So it's at FCC. So what can happen is that the compiler actually reorders your variable on the stack depending on optimization or security requirements. So here we have our double variable F here. And below this, our compiler now allocates N first, so 4 bytes for N. And below that, there's 1 byte just for our character G. And this might be completely different on your computer, depending on your compiler, on your settings of the compiler, and so on. But this was just meant to have you explore this stuff. So essentially, there are no wrong or right answers here, but just, finding out was what my intention here was. All right. So the next question, part C, was what confused some of you because, we were a bit imprecise in asking this question. So the question here was, why is a global variable located at a completely different address? And the question, of course, legally was completely different from what? Yes, well, completely different from a local address. That was what I meant. So sorry if that was unclear. And this is probably obvious because we know local variables are located on the stack. So the stack grows downward from high addresses, which is hexadecimal 7, and a lot of Fs, which is a high address. The rest of the memory address space is reserved for the kernel. Whereas the data and BSS segment for global variables start lower in memory. So usually after the text segment here, it's OX55 something. So we see our local variables are here on the stack with OX7FF something, and our global variables are lower in memory at a lower address, OX55. Now, in the operating system slides, we've shown that, well, our virtual memory starts at address 0, so what's going on here? So modern Linux systems do it a bit differently, so an executable program is not necessarily loaded at virtual memory address 0, but at a higher address, which might be randomized for security reasons. If you're interested in the exact addresses your functions main and sum n are located, you can also use this printf of a pointer to print the addresses of main and of sum n. So that works the same as when printing addresses of a variable. So let's go to our part D. And D was just asking something about the stack again. So why does the address of a local variable in the recursive function decrease the higher the level of recursion is? Well, we've actually seen this before. So we know our stack grows downwards. So it was a bit redundant, but I wanted you to experiment a bit more with this. So let's say we have added a variable e here to our recursive function sum n. So whenever we call sum n recursively again, a new stack frame is allocated. And since the stack grows downwards, the address of the new stack frame is lower than the address of the previous stack frame. So we see with each recursion here, our address is decremented, in this case by CEDF 48 bytes, if I'm not mistaken. So hexadecimal 30. So a stack frame is a bit bigger, so there's more on the stack frame than we've shown. We've simplified this a bit, but essentially you see that the stack always grows downwards, and you can imagine if you do lots and lots of recursions, obviously, you end at an address which is no longer valid, because even if your stack was unlimited, you would actually eventually overwrite your data segment or your BSS segment, or if you have a heap, your allocated heap. And then, of course, you would just corrupt data. And if you tried this, your operating system would actually try to keep you from corrupting data. So each recursion level has its own copy of local variables, of return addresses, of parameters stored in the stack frame. The addresses decrease because our stack grows downward. And that's exactly what's happening here. So that was the exercise, and I hope it gave you a bit of more of an insight of how a program execution, so what we call a process in operating system, what happens at runtime when this process is actually run on your CPU. And as I've said, this is relevant obviously for operating systems because you have to take care of memory allocations, of memory protection, and of course for compilers because you have to generate the code that actually works on these stack frames. So that's all from my side for now, and I'll stop the recording